So, in today's lecture, myself, Dr. Ankit Kumar, and I will explain in today's lecture Euler's modified method concept. So, in today's lecture, I will describe how we solve the different type of the differential equations by using the Euler's modified method. So, what is the learning objectives? Understand understand the idea of modified Euler's method. Learn why it is predictor than ordinary Euler's method. Use the predictor and corrector formulas. Solve an initial value problem. So this is given by dy by dx. Dy by dx is equal to fxy. So this is the standard form, standard differential equation form, which is provided in the questions. Okay. So here this is fxy means it is a function of xy. Okay, it is a function of xy, and this is the first order differential equation, first order derivative. So in Euler method we use only the slope at the beginning of the interval. In modified Euler method we use the average of two slopes, so that the result is usually more accurate. Okay, so in the Euler's method, we use only one slope. That is, what is the formula? Yn plus 1 is equal to yn plus h of f of xn comma yn. This is the formula for Euler's method. And in Euler's modified method, we use two slopes formula. So this is something different. Suppose we want to find yn plus 1 from xn, from yn, where xn plus 1 is equal to xn plus h. Euler's modified method means yn plus 1 is equal to yn plus h of f of xn comma yn. This is Euler's method. This uses only the slope at xn comma yn. Modified Euler's idea: first predict a rough value using Euler's formula 2. Then improve it by taking the average slope at the beginning point xn comma yn, and predicted point is xn plus 1 comma yn plus 1. So first predict a rough value using Euler's formula. So what's the basic idea of modified Euler's method? First you use this Euler's method. Yn plus 1 is equal to yn plus h of f of xn comma yn. After that you evaluate the point xn yn plus 1 at 0. Okay, so in each step, first you apply this formula, after that you apply this modified Euler's method. Suppose dy by dx is equal to fxy. This is equation is given, and the initial approximation y x naught is equal to y naught is given. So what is the Euler's formula is yn plus 1 is equal to yn plus h of f of xn comma yn. So from using this formula we evaluate yn plus 1 at point 0. Okay, then predicted then corrected formula is yn plus 1 r plus 1 is equal to yn plus h by 2 f of xn comma yn plus f of xn plus 1 comma yn plus 1 r, where r is 0 1 2 up to dot. Okay. So this is yn plus 1 is equal to yn plus h by 2. This is the slope, this is again the slope, and we take the arithmetic mean, a plus b divided by 2. So yn plus 1 r plus 1 is equal to yn plus h by 2 f of xn comma yn plus f of xn plus 1 comma yn plus 1 r. If we put here r is equal to 0, then yn plus 1 r 0, so yn plus 1 1 is equal to yn h by 2 fxn comma yn plus f of xn comma 1 yn plus 1 into 0. So yn plus 1 0 means that value, that numerical value. Okay, so here from here we evaluate the we put here n is equal to 0, so y1. So y1 is nothing but this. Y0 is given, h by 2 h is given, x0 comma y0 is given, x0 y0 is given from here, x0 x if we put then x1. So x1 is value is you obtained by, if you add x0 plus h, then you obtain x1 comma y1 value is, y1 value is nothing but y1 at 0 value is here this. So all the 4-5 values are given to you, and then you find the iteration y n plus 1. Okay, then if you put y at 2, then you get next value. So continue correction until two successive values agree to the required decimal places. Continue correction until two successive value agrees to the required decimal places. So you continue your process until and unless you obtain the accuracy of the two decimal places. If two iterative values having the same values after two places of the decimal values, then you says that this value is correct. Okay, so this is the main idea of the Euler's modified method. So first one is, again we will define dy by dx is equal to f of xy, yx naught is equal to y naught. Okay, and then you apply the formula yn plus 1 0 is equal to yn plus h of f of xn comma yn. Okay, after that yn plus 1 r plus 1 is equal to yn plus h by 2 f of xn comma yn plus f of xn plus 1 comma yn plus 1 into r. So this is formula, you remember this formula. Okay, this is some difficult formula, some little bit difficult, but you can remember this. So start with one approximation, this yn plus 1 yn plus 1. So this is yn plus 1 at 1, yn plus 1 at 2, yn plus 1 at 3. Okay, when the values becomes stable, means if yn plus 1 value is equal to the yn plus 1 value at 3, yn plus 1 value at 2 iteration, at second iteration is equal to yn plus 1 value at third iteration. If both the values are equal, you equate from two decimal places. Okay, so if both the values are equal, then you declare that this is the correct value, this is the solution of the differential equation. So solve numerically. Dy by dx plus dy by dx y plus ex is equal to y0 is equal to 0. For x is equal to 0.4, using modified Euler's method with h is equal to 0.2. So fxy is equal to y plus e to the power x. Okay, this information is given. You evaluate your function dy by dx is equal to fxy. So f of x comma y is equal to y plus e to the power x. y0 is equal to 0 is given, meaning thereby this is initial condition. y0 is 0 and x0 is 0. So this is nothing but x0. This is x0, and this value is y0. Okay, so x0 y0 values is given, this value is fxy. F of x of y. Okay, so this is given here. So fxy is equal to y plus e to the power x, it is given here. H is equal to 0.2 given here. So y at 0.2 and y at 0.4. Okay, we must find. Okay, so initial value x0 0 is 0, y0 0 is given. Okay, Now here in this is written useful values e naught 0 is equal to 1, because if you put 0 e naught 0 1, e at 0.2 is 1.2214. You can evaluate this from the your calculator. E is 0.4 is equal to 1.91 1.4918. Now first we evaluate f at x naught y naught, f of x naught y naught. So x naught value is 0, y naught value is 0. So here if we put 0 plus e to the power 0 1, so overall value is 1. So this thing is correct. Now y1 0 is equal to y naught plus h of f of x naught comma y naught is equal to 0 plus 0.21 is equal to 0.2. Okay. Now y10 is y naught plus h of f of x naught comma y naught. So y naught is 0 plus h value is 0.2 and f of x naught y naught this value we evaluate 1. So we put here 1. So overall value is 0.2. Okay. Now we apply the formula y1. Okay. We evaluate these values at y1 iteration. So this is predicted formula predict and this is corrected iterations. Okay. So y1 at 1. So y naught 0 plus h by 2 means 0.2 by 2. Fx naught y naught 1 plus this is x1. So if you draw this line, this is x naught values 0. Then we add h is equal to 0.2. So 0 plus 0.2 means 0.2. Okay. If we add here 0.2 plus 0.2, so this becomes 0.4. Okay, so this is your values. So this value is x naught value. This value is x1. This value is x2. Okay, so x1 value is 0.2 plus e to the power 0.2. x1 plus y1 at 1, y1 at 0. So y1 at 0 means this is, you can see here, xn plus 1 comma yn plus 1. So xn plus 1 means f of x1. F of x1 means 0.2. Okay, 0.2 comma yn plus 1 means y1 at 0. So this is also 0.2 na. This is also 0.2. Why this is also 0.2? It is we evaluated from straight line this x1 0.2 and this is x, this is this y1 at 0. So y1 at 0 is 0.2. You evaluate y1 at 0.2. So this is 0.2 0.2. Okay, 0.2 0.2. So what is the value of 0.2 0.2 is 0.2 plus e to the power 0.2. This value is 0.2 plus e to the power 0.2. This value. Okay, so this value is there. So you if you solve this 0.2 by 2 0.1 1 plus 0.2 e to the power 0.2 value is 1.2214. So you put all these values and then you evaluate 0.24. Okay, then y1 at 2. So y1 at 2 means this is y1 at 2 means y not y1 y1. So y1 at 2. So y1 at 2 means y naught. This is y1 0.2 by 2. This is 1 plus. Then this is 0.2421. So 0.2421 e to the power 0.2421. So this is 1.2214. 1.2214. So you put 0.246 and similarly you evaluate y1 at 3. Okay. So first you evaluate this one, and this y1 at 1, y1 at 2, y1 at 3. So if you evaluate, then you find that this is 0.2464. First value is 0.2421, second value is 0.2464, and third value is 0.2468. Then you can examine that 0.24, 0.24, 0.24. In all the three iterations, the decimal values, the two decimal place values after the decimal are equal. Hence, we can declare that y is equal to 0.2 is 0.246 is a approximate value of this differential equation at point 0.2. Okay, the meaning there, what is we will what we will done we have done is, this is x naught, y naught is given at x naught value, here y naught is given 0. Okay, so this is given, we evaluate at this point what is the value of y1. Okay, so we evaluated that at 0.2. 0.2 means x naught is given, we evaluated at x1 on the real line. Okay, so this is becomes 0.2468. 2468. Okay, so this is the methodology says that, suppose initial approximation of differential equation is given, then you evaluate further iterations, that what is the value at x1, what is the value at x2, what is the value of x3. This is a numerical integration, numerical solution of the differentials. Otherwise, you can easily solve dy by dx upon what is the, if this is given, what is the value of given, y plus e to the power x. So you cannot able to solve this y plus e to the power x. Okay, because if we solve dy by dx, dy by dx minus y is equal to e to the power x. Okay, so here p and q are function of x only. Okay, so what is the value? If we solve this, then the integrating factor is, this is first order differential equation, so integrating factor is e is equal to e to the power minus dx. Okay, so this becomes e to the power minus x. Okay, so this is integrating factor, so y into e to the power minus x is equal to q, means e to the power x, into e to the power minus x means 0 and e1 means dx plus c plus c. Okay, so this becomes y e to the power minus x is equal to x plus c. Dx integration is x, so y is equal to x e to the power x plus c e to the power x, c e to the power x. So we can divide by e to the power minus x left hand side. So put y0 is equal to 0. y0 is equal to 0. So if you put y is equal to 0, then 0, and this is, if you put x e to the power x here, x in place of x you put 0, then this becomes 0 plus c. E to the power 0 means 1, so c. So what is the value of c is 0. So what is the solution? Solution is y is equal to x e to the power x. Okay. What is written here? Actually it is written here y is function of x, na? So y x is equal to x e to the power x is written. So if you put value y is equal to 0.2, so this is 0.2 e to the power 0.2. Okay, you evaluate this quantity by calculator, and what is declare that this is the exact value of y is at 0.2. So you can check whether this value is correct or not. If this is 0.2468 and you obtain 0.58, then this is okay. Okay, if this is, there is much more difference, then your value is wrong. So you, if you solve the exact method and then you compare your numerical values, because this is the numerical value. In numerical values some error is found, but in exact solution, differential equation solutions, you cannot find any error. This is the exact value. Okay, so this is a method of finding the exact solution of the differential equation, and this is the numerical solution. So we have evaluated y1 at 4 iteration. Now we declare that y at 1 is value is 0.2468. Now we find f of x1 comma y1. So this is 0.2468 plus e to the power 0.2. Okay, because this is 0.2 and this is this. Function is y plus e to the power x, so ये 1.4682. Now y2 0. So what is the value at y2 0 is y1 plus h of f of xn comma y1. This value. Okay, yn plus 1 is equal to yn plus h of f of xn comma yn. So y2 is y1 plus h of f of xn comma y1. So y2 0 is 0.2468 plus 0.2. This is h value and this is 1.4682. You have evaluated the here. Okay, so this. So if you check, then you obtain 0.540, and this is 0.2468, 0.2 by 2. So this is 1.4682 and 0.540. So you evaluate in a similar manner. Similarly, you evaluate y2. So you obtain that 0.60 and 0.60 and here 0.60, meaning thereby the value is accurate within the 2 decimal places. So we declare that y at 0.4 is 0.6031, meaning thereby here you obtain y not 0 is 0 given, you evaluate y1 is 0.2468. Here you declare that y2, so y2 is equal to 0.60. 0.60 is given. Okay, so y2 is equal to 0.60 is given. So this is the methodology, meaning whereby you divide each step. This is something long process, and this is very important method also. So for each step, you first define predictor y1 values. After that, correct iterations. You correct iterations. Then again you define for x1. You evaluate if x1 y1, y2, at 0, then you y2 1, y2 2, y2 3, and y2 4. Then you declare that things. So the final answer and teaching remarks. What is the final answer in this 0.2 and 0.6031? Why is this method better than Euler's method? What is its important? Why we study this? So Euler's method uses only one slope. Euler's method uses only one slope. Modified Euler's method uses the average of two slopes. Okay, hence it is usually gives a better approximation. Okay, predictors gives a rough value. Predictors gives a rough value, and corrector improves the value. Repeat until the value becomes stable. This is very important part. It is written here that if you write here yn plus 1 yn plus 1 is equal to yn plus h of f of xn comma yn. Okay, so this is nothing but Euler's method. This is nothing but predictors. This is here denoted as predictor, meaning that by if we evaluate, suppose y0 y0 is equal to x0 is given, y0 is 0, it is given, and x0 is given. Okay, so if you evaluate y1, then y0 plus h of f of x0 y0, you evaluate and then you jump the second iteration. But in this method, in the modified Euler's method, you evaluate using this, then you apply again the formula yn plus 1 yn plus 1 to the power r plus 1 is equal to yn plus h by 2 f of xn comma yn plus f of xn comma yn xn plus 1 xn plus 1 comma yn plus 1, okay, to the power r plus 1 to the power r. Okay, this is the 1 minute. I will check this again. Xn plus 1 yn plus 1 into the power r. Okay, so this formula is correct. And plus 1, this is. So if you put the values, you evaluate y1 from this formula, then you check y1, then you check the stability of the y1, that it is in at what point it is stable. Okay, so stability checking analysis formula is that this is predictor formula, and this is predictor formula, this is corrector iteration formula. So you check, you correct the iterations that at this point this is the stable solution of the differential equation. This is the correct value. Okay, that if this is declared, then you move on the next iteration, yn plus 1, this is y1, and then you evaluate y2 by similar method, y3 and y4 and so on. So this method is very helpful. Okay, so this method is sometimes large method, but if you practice more and more, then you easily cover this method. Because in this method, if you learn this method, then you learn two methods. Means one is the Euler's method, and second one is the Euler's modified method. Because in the Euler's method is inbuilt. So if you practice this method, then you always this, and you also remember this formula or Euler's modified and Euler's method. If question is coming, you write the formula and you get the marks for the formula also. Okay, so this is the methodology section. So in today's we will end up here, but in the second class, application of Euler's modified method. This is not very. This is also repeated, and then RK method. Okay, I will describe the RK method in 2 or 3 classes, and then you can easily cover these topics. Okay. So this is Euler's modified method, applications of Euler's modified method. So we describe the Euler's modified method in the next class. So thank you very much for listening this class. If you have any doubt, then you can ask me. This is modified Euler's method. Okay.
Hello.